Today is the fourth, the number 4 seminars of the coastal zone risk mitigation and management working group, which will be given by Professor Qinglan Li. Professor Li, she's a professor at the Shenzhen Institute of Advanced Technology of the Chinese Academy of Sciences. She got her bachelor degree, went to undergraduate program at the Tianjin University in northern China. Afterward, working as an engineer for 10 years or so, she went to Canada to do her master degree at the McGill University. And then from then, she went to Hong Kong to get her PhD degree at the University of Hong Kong. And after graduation in 2010, she worked for a short time at the company called AECOM Asia before she joined the Shenzhen Institute of Advanced Technology in 2011. And as you would hear from her, her specialty is in the quantitative forecast of wind and rainfall induced by tropical storms. Actually, tropical cyclones or tropical typhoons. Of course, this is a very important topic in our region, especially in southern China, so to say. And she has won a number of awards, including the Key Technical Talent of the Chinese Academy of Sciences in 2018, and the China Industry University Research Corporation Innovation Award in 2020, and more recently, the Shenzhen Science and Technology Innovation Award in 2021. Professor Li, please start your talk. Thank you so much.
Okay. Thanks for the kind introduction. Hello, everyone. I'm Qinglan Li from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. I'm very honored to share our study of tropical cyclone intensity prediction in the Western North Pacific. This talk mainly cover 2 papers, which this work has been done during the past almost 10 years, and this work is an ongoing one. Okay, eventually I will share some my future thought of my next plan in the end of my talk. So the 2 papers follow the same outline. The first background and the data and the methodology, and then a present result and discussion, and finally make conclusions. And so the first paper, the title is Statistical Regression. Okay, how to, oh, yes. Well, okay, the first paper, the title for the first paper is Statistical Regression Scheme for Intensity Prediction of Tropical Cyclone in the Northwestern Pacific. This paper was published in 2018 in Weather and Forecasting. The coast area of the South China is very vulnerable to the TC tech. Every year, the economy loss in Guangdong province induced by tropical cyclone exceeds more than 1 billion yuan. So the timely and accurately forecasting the TC intensity is very crucial for for the for TC prevention disaster, for TC disaster prevention. The study area, this figure show the study area. It mainly cover the area north 0 degree, north of 0 degree and the west of 100 degree west. And this figure show the check of this figure. Oh, we use the best check data from Shanghai Typhoon Institute and Joint Typhoon Warning Center. And this figure show the check of the TC in the Western North Pacific from 2000 to 2015. And this check from the Shanghai Typhoon Institute with 6-hour interval, and the background, the data of the background is obtained from NSAT, and the sea surface temperature is obtained from NOAA. We use the first 12 years of model calibration and the remaining 4 years for model validation. In China, the Chinese meteorological administration define the TC intensity by using the maximum sustained wind 2 minutes, the maximum 2 minutes average wind to define the TC intensity, while the JTWC use the maximum sustained in 1 minute, the average wind to define the TC intensity. If the TC intensity are from the same source, the 1 minute sustained, the maximum 1 minute sustained wind should be always greater than the 2 minutes average means wind. However, from this figure, which compare the TC intensity between JTWC and STI, we can see that for most of the time, the intensity defined by JTWC is greater than STI. However, for some case, the intensity from STI is greater than the intensity defined by JTWC. That means the TC intensity from the two sources are not the same. There's uncertainty for TC intensity estimation. That's why we use the two TC, the best check data from two administration, STI and the JTWC. The most important innovation for our study is we propose an index, which we call it sea land ratio. The sea land ratio quantify the underlying surface of the tropical cyclone. We define, for example, for a TC center, we define an area of 500 radius. With the 500 radius, the circle within the 500 diagram of the radius circle, the area of the seawater arrow divided by the whole circle is, we call it sea land ratio. We calculate all the sea land ratio along the China coastline, and we find the medium and mean value of the sea land ratio along the China coastline are all are equal to 0.5. Therefore, we define, then we have according to the definition, based on this figure, we can see that the A is is defined as the TC sample near coast. And for the sea land ratio greater than almost or equal to 1 or greater than 0.999, then this sample is called the TC is over the open ocean. When the sea land ratio is less than 0.5, that means the TC is already over land. And when the sea land ratio is greater than 0.5 and less than 1, then we call it this TC is near coast. Based on the definition of the sample over land, near coast, and over ocean basin, we have this. We separate, classify this sample, TC sample, to samples over land, near coast, and over ocean basin. Why we choose the radius as 500? Because if we choose the radius of 600, but then we will have more samples of the near coast. If we choose the radius of less than 500, for example, 400, then we will have more samples of the TC over ocean to keep the balance of the sample over land, near coast, and over ocean basin. That's why we choose the radius of 500 as the criteria to define the sea land ratio. And this table shows the sample number for different TC groups. And this first column is the forecasting leading time. We will try to forecast the TC intensity for future 12 hours, 24 hours until 72 hours. We develop our model based on multiple linear regression. This equation is the function. Show the multiple linear regression function. And the potential predictor for the regression model are listed in this table. And this includes the persistent climatology variables such as latitude, longitude, and Julia date, because this is the to show the location, and the Julia date show the time, show the date. And there are other synoptic variables which reflect the condition of the atmosphere, such as the dV max and the vertical wind shear and SST and POT, etc. And this table shows the selection of the significant variables in the model. And the 0 means, because we have two data resource, one is from Y. Okay, the Y is the future TC intensity change. And the Y, we have two sources from, one is from, as I mentioned before, one is from Shanghai Institute and the other is from JTWC. And in the table here, if there's the number of 0 means this variable is not selected by both prediction model. If the number 1 refers, this variable is selected by the prediction model for STI data sets, and the number 2 means the variable is selected by the prediction model from the JTWC data sets. The number 3 means these variables is selected by both prediction model of the data sets. So here we can see that the dV max and POT and SHRD are selected by both prediction model. then let's see what's the dV max and what are these significant variables, what are they? And the dV max means the intensity change during the previous 12 hours. SHRD is the vertical wind shear of the deep layer. Usually it's the vertical wind shear equal to the vertical difference between 200 H bar minus the 850 H bar. But in our study, we follow the previous study of one study. We compute the vertical wind shear at 1,300 H bar. And the POT is the maximum possible intensity minus the initial intensity. POT is a function of the SST. So because this POT square is similar to the POT. So let's look at what's the detailed relationship between these three variables and the intensity change. Let's look at the dV max. The dV max, as the definition, is the intensity change during the previous 12 hours. And the first column refers to the TC intensity near coast, and the right column refers to the TC intensity over the ocean, in the ocean basin. The blue color means the intensity, the negative change of the intensity which means the intensity will decrease. And the red color means the positive change, means the intensity will increase. And first of all, we look at the black color means the intensity will not have no change. From this figure, we can see that more than 95% of the 12-hour TC intensity change is within 10 meters per second. That means the whole, the possibility, or the whole distribution is within 95% is within 10 minutes per second. And let's see that the future TC for the TC intensity for short time for the first line is for 12 hours, and the second line is for 24 hours, then 36 hours and 48 hours, etc. Then let's look at for the short time, 12 hours and 24 hours. The TC intensity will be more dominant by the previous 12 hours intensity change. For the previous, in case of the negative change, when the dV max is negative, then TC, the possibility of the black, the blue bar is has higher possibility than the red bar. And with time increase, we can see that when the TC near the coast, when the time is more than 36 hours, then the blue bar is the possibility of the blue bar increase. With the time increase, the TC intensity change becomes uncertain, especially for TC near coast with positive dV max, and for TC when the TC is in the ocean basin with negative dV max, and with the time increase, the you can see that the possibility of the blue bar and red bar, the possibility is almost the same. And that means with the time increase, the intensity change will becomes uncertain. For the POT, the definition of the POT is the maximum possible intensity minus initial intensity. This is a function of the SST. For the threshold, that means the threshold for the TC near coast and over the open ocean are different. For the near coast, the threshold for TC intensity change, increase or decrease, the threshold is 50 meter per second. That means when the POT is less than 15 meter per second, then for the TC near the coast, only when the POT is more than 15 meter per second, the TC will have higher possibility to increase. However, when the TC is in the ocean basin, the TC, the threshold for TC intensity to increase, the threshold is only 14 meter per second. That means it is easy for TC intensity to get stronger when they are over the open ocean. SHRD is the vertical wind shear. Vertical wind shear is a significant variables to control to dominant TC. How TC can get increase or the intensity will increase or decrease. Let's look at the enlarged panel. When TC are near the coast, the threshold for SHRD is 15 meter per second. That means when the vertical wind shear is less than for the near coast sample, when the threshold is 10 meter per second, and for the TC over the open ocean, the threshold is 15 meter per second. This is a different criteria for the TC to get stronger, have a different criteria. As I mentioned before, in our study, we propose a new index of sea land ratio. So let's further investigate how the relationship between the sea land ratio and the intensity change. This figure show that for near coast, then when the sea land ratio is greater than 0.9, the TC also have higher possibility to get stronger. And when the sea land ratio is less than 0.9, more possibility we can see more possibility of the blue bar. And for the TC after landing, most of the time, the blue bar dominant the possibility. as I mentioned, that in our model, we for the calibration and validation, it's compare the performance of the model. And this look at this figure show the performance, and for the R-square, for the during the calibration period, when adding sea-land ratio, the R-square is higher, is bigger than the calibration without sea-land ratio. And during the for the MAE, we can see that for most of the time with the sea-land ratio, the MAE is less than the error for the model without sea-land ratio. And this is the performance. This is the comparison based on the STI datasets. And for the datasets of the JTWC, we have similar result. You can see that with the sea-land ratio, the model has higher R-square than the model performance without the sea-land ratio. And overall, with the sea-land ratio, the R-square has increased 3 to 5%, and the MAE and root mean square error has decreased 2%. Then let's compare the similar model with our pair researchers, and this table is obtained from the NAF study. We have the same. They use the similar predictors to forecast the TC intensity in North Pacific, and we can see that for R-square, the R-square values for 12 hours is around 0.4, and in our study in the overall, because this model is only for the intensity forecast over the ocean basin, and we can compare that for 12 hours the model's R-square is 0.4, and for 24 hours the R-square is 0.5. And compared to our model, we can see that for 12 hours, the R-square is around 0.5, and for 12 hours, the R-square is around 0.6. So our model performance is better than the USA model, the STIPS model. And for forecasting the TC intensity after TC landfall, there's NAF and Demeria proposed the simple empirical model for predicting the decay of tropical cyclone wind after landfall. They proposed this empirical equation to compute the TC intensity after TC making landfall. And we can see we use this equation to compute the model, to compute how good are the model to forecast the TC intensity after landfall. For the calibration, we can see the performance is fine. However, for the validation, we can see the R-square decrease quickly, and the error, MAE and root mean square error, and increased considerably. That means their model is not good. The performance is not good. And the calibration period is similar to the result presented in the paper. And by comparison, our model perform for the calibration and validation. Our model perform both are fine. both are, and for the validation period, our model performed much better than the empirical model provided by the USA. And this figure show the case study. We use two TC, cellular and the function, and to show the performance. We can see, and generally, our model can capture the variation. The red lines are the data provided by Shanghai Typhoon Institute, and the black lines are the comparison based on the JTWC data sets, and the dashed lines are the model forecast, and the solid lines are the observation provided by both meteorological administration. We can see that generally speaking that our model can capture the TC variation. However, we can see when the TC experience rapid intensification, the performance is not good. And this is the conclusion for the first paper. I will not present in detail. And then next, I will present our second paper, which is published in this year. The title of the paper is Tropical Cyclones Intensity Prediction in the Western North Pacific using Gradient Boosted Regression Tree Model. And this is a machine learning method. And this paper is published in the Frontier in Earth Science. And the background, statistical method usually based on regression may be efficient, or may not be effective in capture nonlinear relationship. Therefore, their forecast result need to be further improved. This is the background. Therefore, in this study, we propose a machine learning method, the GBRT model, to predict the future change of TC intensity in Western North Pacific Ocean. GBRT is good at capturing the complicated and nonlinear relationship between TC intensity change and the other related feature. Again, this figure show the check from Shanghai Typhoon Institute. And in the second paper, the time period is from, we have 20 years, the time period. We use, we separate the data sets into 4 groups according to 5 consecutive years, such as 2000 to 2001, 2005 to 2009, and etc. Then we have 4 groups. We use one group as the testing sets, and the other 3 groups as the training sets. Then we have altogether 4 testing sets. Then we do the cross validation. Then altogether we have 4 testing sets and do the cross validation. Again, the background are obtained from ANSEPT, and different from a previous study. The SST data now are the daily data obtained from NOAA. The previous study we use the SST data is the weekly, not the daily. We use the GBRT to develop to establish the prediction model, and in addition, we use Bayes optimization to optimize to tune the hyper parameters in the model. Again, we use the same same predictor as the previous model, but the difference is in this study we use the machine learning method to handle the nonlinear relationship between the predictor and the predictants. And the advantage of the GBRT model is it can rank the importance to describe the importance of the predictor, and usually this figure only show the first 6 most important variables in the prediction model. For the model predicting the TC intensity overland, we can see the most important predictor is the Vmax. Then the most important variables is dVmax for 12-hour TC intensity change. For again, for the 24-hour TC intensity change, the first 2 important variables are the same as Vmax and dVmax. For TC over the open ocean, the dVmax for 12 hours TC intensity change, the dVmax is the most important, followed by POT and SST. For 12-hour TC intensity in change, the most important variables are POT, followed by dVmax and SST. For TC near coast, for 12-hour TC intensity change, the dVmax is most important, followed by POT and sea land ratio. Then for 24 hours, the most important variables are POT followed by sea land ratio and Vmax, and etc. As I mentioned, that we have the 4 testing data sets and we do the cross validation, and we can see that the R-square for the overland samples, the R-square is very can reach the median of the 4 testing data sets can reach more than 0.65, and for the 24 hours, the R-square can reach 0.75, and the mean absolute error is for the overland samples for 12 hours is around 2 meters per second, and for 24 hours model is around 2.5 meters per second. And these show the near coast, the R-square for the 12-hour is 0.55. And let's recall the previous. Let's see that let's look at the USA, the USA model, the R-square and MAE for 12 hours is for 12 hours, the R-square 0.4 and MAE is around 6 meters per second, and 24 hours, the R-square is 0.5 and MAE is 9 meters per second. And compare the GBRT model, you can see that R-square is record that the MAE for the near coast and over open ocean, the MAE is almost the error is much less than the error obtained by USA model. And this figure show the comparison between GBRT model and the multiple linear. The multiple linear model is the our model obtained by in the first paper. And we can see that the R-square, comparing our own multiple linear regression model, the R-square increased by around 5.5%, and MAE and root mean square error has decreased dramatically, and MAE is decreased around 26%, and root mean square error decreased by 10%. And for case study, we also use Sodilo and Monkhead 2TC, which has influenced China greatly. We show we use these two as the case study. Again, the GBRT model perform good in the TC intensity prediction. And conclusion, a GBRT model can describe well the nonlinear relationship between predictor and predictants. Compare with the multiple linear regression model, R-square of the GBRT model for TC intensity forecast increased by average of 8% for STI model, and increased by around 4.5% for JTWC datasets. MAE and root mean square error has dropped significantly. POT, dVmax, Vmax, SST, and C-land ratio are the most important variables for TC intensity forecasting in the GBRT model. And thanks. So any questions?
Yeah, thank you so much, Professor Lee. Lots of detailed data analysis. Any questions from the audience? You can either raise your hand or just ask Professor Lee. Because you are talking about something that having to do with the rainfall and wind speed.
Yeah. These are the parallel works I have done during the past 10 years. And I have done the wind and rainfall forecasting, because the rain induced by tropical cyclone, because when we develop a model to forecast the wind and rainfall, or we need to consider the intensity. And however, the intensity forecasting provided by the worldwide and globally, the TC intensity prediction has a lot of uncertainty. So we became interested in this study, and we have developed I focused and devoted a lot of time to explore the mechanism or the method. And we have, and also, as I mentioned, it's an ongoing work. And previously, we have considered the underlying surface, such as C-land ratio, and also we have considered the background atmosphere, like the synoptic variables. And in future, we will consider the typhoon. Can you see the slide here? Can you see?
Right. I can see that.
And
yeah.
in future, we will consider in future we will continue to consider the TC itself, like the structure, because in our model we haven't considered the structure. Then currently, I have 2 PhD students working on the TC. We will propose a new variables to quantify the structure of the TC, and we use it as a new variables in the new model. Then we will further increase the forecasting accuracy, and currently we'll have some preliminary work I can share that as I mentioned here, we can see that generally can you see the screen, my screen?
Yes.
Yes. We can see that generally speaking, when the TC experience, I mean the intensity change slowly, the model perform are good. But if the TC experience rapid intensification, the model always, I mean, the performance is not good. For example, at this the period, the TC intensity, the solid lines here is around 70 meters per second. However, the forecast is only 6 or 8. The model cannot capture the rapid intensification. That's why we further think about how to simulate the rapid intensification. Then we find that the rapid intensification is probably the TC structure will have a great influence, the rapid intensification. That's why we consider to adding a new variable which can quantify the symmetric structure of the TC and into the new model. We have some preliminary result, and for the to diagnose whether the TC will experience rapid intensification or not, we have find that the most important variables to explain, to predict whether it will experience rapid intensification or not, we find that the dV max, SST, POT, and the symmetric ratio, as I mentioned, we propose a new ratio. The symmetric ratio is a critical variable to determine if the TC will experience rapid intensification or not.
Yes. May I ask you? Do you compare with, when you compare with the actual observation, where do you get your data? I mean, from which mission or observations?
You mean this satellite data, or
right? Yeah.
This is the satellite data. Fengyun 2.
So it's a Chinese satellite.
Chinese satellite, yeah. Because Fengyun 2, we have long history. And the Fengyun 4, we have Fengyun 4 satellite data, but this data has very short. This is become to work only in 2018. But for Fengyun 2, we have long history, more than 10 years. So we use Fengyun 2 to quantify the asymmetric ratio for the TC structure. And later on, we will probably consider using the new satellite. And we also for another PhD student has working on by using the Japanese satellite data to consider using another method to try to investigate if that method is work or not to diagnose the rapid intensification of TC.
So you said that at the very beginning, you said that the damage because of typhoon, and the financial damage is very high.
Yes.
And which area, which part of the country, has suffered the most, damage?
Usually is USA and China. I think Philippines, of course, because Philippines is very, very small, but China has long coastline. Overall, I think the economic loss in China altogether. I mean, this is the value, the number, the 10 billion yuan is only for Guangdong province. For China, probably every year we have 16 billion yuan.
You say 60 or 16?
60.
60.
Altogether.
Oh, this is a very large number. Yeah.
Yeah. 60. This is only for Guangdong province per year.
So if you make the correct prediction, you save a lot of money.
Yes.
But if you don't, you lose a lot of money.
Yes.
Okay. So any questions from the audience? No. You could. I just turn on your mic and ask Professor Lee.
Okay. I have two questions. First,
can you tell us? Oh, this is Dr. Pan. Yeah.
Yeah, Dongju from the Earth Observatory of Singapore.
Okay.
First, thanks very much, Professor Lee, for your interesting talk. The first question I have is, because the performance of your model is excellent, so have you operationalized your models?
Operationalized, right?
Operationalized your model.
Currently, we are collaborate with the Chinese national meteorological center, and we try to develop our model on their platform. Yes, they are currently we have no operation, but the project is ongoing. We have signed the contract, and have just signed the contract. We will put the GBRT model on their platform.
Oh, great, thank you. Okay, I have another question, because you mentioned it's like US and China are the two countries suffer most from the typhoons. So, because for your study, you're focusing on the Pacific region. So, can your models be applied in other regions, and how will they perform?
Yes.
In other regions. Yeah.
And actually, this okay. This is the comparison. This is the original model is proposed by Demaria or some other USA scientist. In probably the first paper was published in 1994, and later on they proposed their method in North Pacific, which is the original model is called SHIPS, 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 and later on they use that model. They apply that model in North Pacific Ocean, then called the STIPS. And this is this model is applicable all over the world. And so in the model in the first paper, the innovation of my paper is I propose a new index of sea land ratio. The sea land ratio is not the influence of the underlying surface is not considered in the SHIPS and STIPS. Can you?
Okay. Oh, yeah. Thank you very much. That's clear. Okay, I think I have another probably a basic question, because for your regression models, you have a lot of predictors. So I'm assuming all these predictors are independent, right?
Yes, you can. Actually, they are not independent, but we use that the stepwise regression. Then the model or the computer will select the model itself. The computer will consider the relationship between the variables.
Okay.
Now, we can assume the variable are independent, but actually they are not independent.
Okay, thank you. But if if two of them are highly correlated, was it contaminate the predictions, the performance of the predictions? And
if the two variables are highly correlated, the computer usually will only use one
Okay.
variables and exclude the other one.
Okay, great. Thank you. Thank you very much.
Okay, thank you.
Yes, thank you. Any other questions from the audience? I mean, please, we still have a little bit more time.
May I ask one question, please?
Yes,
Yes.
please.
Okay, thank you. Thank you for your excellent presentations. It's covered lots of things. I would like to know regarding the anticipated actions of typhoon, or you can say in our region it is called cyclones. Some other regions it is hurricane. So, like there is some genesis parameter like sea level pressure, sea surface temperature, tropical cyclone heat potential, and for the landfall, wind speed, rainfall are very much important. So how we can determine for the anticipated action related initiative, trigger and threshold of those parameters? Or is there any sophisticated method for that? Or any references, please?
I'm sorry, Professor Ye, have you catch what the audience?
Okay, I read what he wrote. Let me see. Going back. Can you see the chat box? Say for typhoon anticipatory action, which method will be helpful to determine genesis? And there's SLP, SST, TCHP, and landfall. Yeah, wind speed, rainfall, trigger, and threshold.
For typhoon action, which method will be helpful to determine genesis? And landfall trigger and threshold. Genesis. Oh, yes. You mean genesis? Genesis, I think the most important. Which method will be helpful to determine genesis? SST, TCHP. TCHP is also for genesis. The most important is SST.
Just 1 minute. Actually, all three things are important. I would like to know for like if SLP is reducing, SST is increasing. So this kind of relationship is there. Exactly for like in the Pacific Ocean, Pacific Basin, Northwest Pacific Basin, there is a depression. So for 5 days advance, how we can determine what would be the possible SLP, sea level pressure, or what would be the possible SST? SST is, of course, a state. So how we can determine at least 5 days advance or 6 days advance by any methods? And when it occurred very close to the coast, then wind speed will be higher. There is a possibility of very much rainfall. So what would be the possible rainfall? And to determine those kinds of advanced forecasting, is there any sophisticated training methods? I think you catch my point, please.
The reference determine the typhoon genesis and threshold and trigger. Determine.
Like different typhoon has different sea level pressure, right? Different typhoon has different wind speed, different rainfall. It is not similar for all typhoon.
No.
How? Yeah. So how advanced we can determine, and how advanced we can tell that this mass of wind speed will be there. So it may be 30, 40, 50. Yeah.
Okay. So in our model, we only forecast for TC intensity. We only forecast consider the TC intensity change for the future 3 days. And as I mentioned, we have we can forecast 12 hours until 72 hours, means 3 days in advance. We have 72 hours the leading forecasting time. Usually, people probably nowadays more meteorological agency will consider forecasting the TC intensity in 5 days in advance, but the error is much high. In our study, we'll only consider 3 days in advance. But usually, we can see that the error will increase with for the MAE.
The time.
Yeah.
Yeah.
For the MAE, the error will increase with the increase of the forecasting leading time. Yes.
Right.
Yeah, but then you mentioned that for 5 days in advance, probably some agency can do that, but in our study we don't consider that long time. We only consider 3 days in advance.
I think 3 days is good. 3 days for 72 hours is the very perfect, because increasing time, increasing error. So for 48 hours to 78 2 hours is very perfect for taking initiative for the disaster management. So anticipatory action is only for the management for the coastal people. So how vulnerable those people, how advanced we need to give the forecast to the people. So accordingly, forecast-based financing or relevant initiative can be taken by the disaster management authority. So that's why we need to give the information to the policymaker. By this typhoon, there is a possibility of this category, this much of rainfall possibility of these regions. So that's why we need to give some precise information at least 48 hours advance.
Yeah.
So that's why I'm asking, is there any sophisticated tools or method for that?
Yeah,
I think now you understand the purpose.
Yeah, if for the rainfall and wind speed forecasting, I think the 24 hours, the accurate forecasting of the wind and rainfall forecast in accurate forecasting with 24 hours forecasting in advance, I think is enough for the management, risk management.
Right.
Yeah, 24 hours
Exactly.
is enough.
Yes.
Mhm.
Yes. Thank you.
Thank you.
Thank you very much.
Now, this is a very useful discussion, and then but I have a question. One thing that I wrote down Dr. Lee's email address.
Mhm.
I hope you don't mind. If you have further questions, you could write to her. Yeah, I'm sure she'll be happy to send you her papers to read. The other thing is that Dr. Das, I see that you have this NOAMI. Is this an institute's name?
Oh, yeah, it is the National Oceanographic and Maritime Institute. National Oceanographic and Maritime Institute.
And in India?
In Bangladesh.
In Bangladesh. Oh, great.
Yes.
Now, I wrote down my email address. Okay.
Yeah. I will send you an email.
Can you send me an email? Because
Yes.
I would very much like to invite you to give a talk.
Oh, thank you very much. Thank you.
Yeah,
Oh,
please.
it's so kind of you.
Yeah, please write me down your email address, right? So I could
Yeah, I'm
write to you.
writing.
Yeah,
Yeah.
I think we need such a discussion, and it's very, 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 very interesting, very important also. Because this is the
Yes, sure.
real purpose of having this working group. So now any other one has questions to Dr. Lee or to Dr. Das as a matter of fact. And I think we could have a dialogue here. If not, I would thank okay, no, there's no question, nothing on the chat box. So I think we could close the session for this time. Dr. Lee, thank you so much.
Thank you.
Yeah. I mean, I hope that you would participate and continue to attend our workshop and give your important suggestion and advice too. Yeah.
Sure.
And I think this is a very vital work. And also thank Dr. Pang for joining this question and everybody else. I hope to see you again next time.
See you.
Please check our webpage, our announcement, and that we will have, I think about every month we will have a seminar like this. And I welcome you. If you're interested in joining the working group, please also write to me. Yeah, thank you so much.
Thank you.
Yeah, bye-bye.
Bye-bye.
So my email is there. Thank you.
Thank you.
Thank you. Good presentation.
Okay, I see it. Yeah. So anyone want to give a talk, you know? I mean, please write down your email just and send it to me. All right. And this young lady, you want me to invite you to give a talk?
Hello, Professor.
Hello.
Thank you. I so enjoy. I come from NCU, Taiwan.
Mm. So so you just, you know, if you want to reach me, you know, just write me a note, right? Okay.
All right.
Thank you. Yeah.
Thank
You're very
you.
welcome.
Bye.
Yeah. Bye-bye.